All right, we last left off in Chapter 1, Section 2, talking about the different transformations of parent functions and their graphs. We talked about translation, which moves it left, right, up, down, and that was adding or subtracting to the back of the equation. We talked about reflection, which flips it up and upside down, or reflects it or mirrors it over a line. We looked at mirroring it in the x-axis, using the x-axis as the mirror. That was the line of reflection. Today we're going to talk about dilation, okay, or changing the size of the graph. Another way to transform the graph of a function is to multiply all of the y-coordinates by the same positive factor. The reason they say positive factor is because the positive and negative part doesn't have anything to do with the dilation. It has to do with the reflection. So if you use a number greater than 1, or the absolute value of a number greater than 1, then it's going to be a stretch vertically. It's like you're pulling on the top of that graph and you're stretching it, which is going to make it look more, it's going to skinny up. It's going to get more skinny. If you use something between 0 and 1, a fraction or a decimal, a true fraction or decimal, not like 1.5, that's got a decimal on it, but that's not a fractional piece. We're talking between 0 and 1, then it's going to compress or vertically shrink. Vertically compress is the word I like better instead of shrink. Shrink makes you think it's going to get smaller. It actually ends up looking wider. So if you compress something, it ends up squeezing out the sides of it and gets wider. And that's kind of what I like to do instead of shrink. So I kind of like to say or compress, because we're going to squish it down. Okay, we've got some pictures over here on the side that kind of tell us that sort of thing. So let's look at it actually happening here in some graphs. We're going to graph each function and the parent and then describe the transformation. So I always like to have 5 points. And this one we're going to graph, it's going to be y equals 2 times the absolute value of x. Okay, so I'm going to graph, again, -2, -1, 0, 1, and 2. Now if I plug in -2, the absolute value is 2, times 2 makes it 4. Absolute value 1 is 1, times 2 is 2, 0 is 0, 1 is 1 times 2 is 2, and then 2, the absolute value is 2, times 2 makes 4. So I can graph those points, -2, 1, 2, 3, 4, -1, 2, 0, 0, and I'm going to be the same on both sides. This way. Those lines are pretty close. And then we're going to do an XY chart for the parent. The parent graph is just the absolute value of x. You need to go back to that front page and remember all the different parent graphs. This is an absolute value. It's a v. The parent graph is just the absolute value of x. I'm still going to use -2, -1, 0, 1, and 2 because that's right around the vertex. I want to make sure I see both sides of the v. So this right here is my vertex point. It's right in the middle, and you'll see that it V's around the vertex. You get kind of mirror images of each other because they're exactly the same distance away. Those two x's give you the same y. So if we put in -2 here, we get a +2. Put in -1, we get a +1. 0 is 0, 1 is 1, 2 is 2. So let's graph those. I'm going to graph them in a different color so you can see the difference. So -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. So this graph goes out this way. Okay, so this one is green here. I'll put the green on the thing here. So the difference between the parent in green and what we can call the kid, or the transformed graph in red, is it looks like it's been squished in sideways. It's gotten skinnier. So what has happened is we've had a stretch vertically by a factor of 2. And that factor of 2 is right here. There's the 2. So things out in front of the equation that we have are going to multiply that y value by that number. It's going to stretch or compress. So if it's above 1, like 2 is, that's going to be a stretch, so it's gotten skinnier. All right, we've stretched it upwards. Okay, so let's look at h of x equals 1/2 x squared. I'm going to need an xy chart. This one's going to be the 1/2 x squared. And I'm going to do -2, -1, 0, 1, and 2 again. If I square -2, it becomes 4. Half of 4 is 2. If I square -1, it becomes +1. +1 times 1/2 is still 1/2. 0 times anything is 0. 0 squared is 0. 0 times anything is 0. 1, it should be 1/2. If I do it again, see 1 squared is 1. 1 times 1/2 is 1/2. 2 squared is 4. 4 times 1/2 is 2. Half of 4 is 2. And I still see that mirroring there. So starting at 0, 0. Go out to 1, go up 1/2. Just right in between there. Go out to 2, go up to 2. Go back -2, up to 2. So there's my graph there. So it gets this kind of curve this way. Now I'm going to draw the parent. I'll do that in a different color all the way this time so you can see the difference. The parent is just x squared. And go -2, -1, 0, 1, and 2. Now you don't have to pick those. If you didn't want to have to deal with the halves, you could have counted by 2s. That would have worked, and you would have probably gotten whole numbers all the way up, because if you do -3, that's a 9. Half a 9 is a decimal or a fraction. But if you do 4, 16, 16 has a half that's nice and whole. It's an 8. So you could have counted by 2s there. This one, -2 squared comes 4. -1 squared, 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. Then we graph them. 0, 0. 1, 1. 2, 4. -2, 4. And if you notice, the parent is inside, the kid or the transform graph is outside, and it's been widened. So it's been squished down and pushed out wider. So we could say that is compressed. They would say shrunk. I like compressed better. It makes me think more of squishing out the size. Compressed vertically by a factor of 1/2. That's what's happened to it. So we've talked about 3 different types of transformations. We've talked about translation, left, right, up, down, mainly the up, down. We'll talk about the left, right on the next problem. We've talked about reflection, where you negate that thing out, you negate it in front, and that flips that y over the x-axis to the other side. That's a reflection. And then we've looked at now dilations. That number in front, multiplying and stretching it up, making it skinny, or compressing it down and making it wider. So let's look at a combination. We can put more than one of those change in at the same time. So using a graphing calculator, and this is mainly to give you the chart that you need. It helps out. You can do it by hand, by calculator, by brain, but if you have the graphing calculator, you can get the XY chart pretty nice and easy. I'm going to show you on Desmos. So use a graphing calculator to graph g of x equals negative absolute value x plus 5 minus 3 and its parent, and describe. That's the same thing we've been doing on every problem. Graph, graph, describe. So we're going to do that again. Now I can already tell certain things. I can already tell from right here that that is a reflection. And I can already tell right here that it's been moved down 3. I'm not really sure what that one is, but I should be able to see it pretty soon. So let's give it a graph. I got x, got y, gonna make my chart. And before I make my chart, I'm actually gonna graph it on the graphing calculator. So I'm gonna move to what's called Desmos, D-E-S-M-O-S. And I'm gonna type in the exact thing, y equals negative absolute value, x plus 5. And I like, as I do this, it's showing me the graph over to the right of how it's been moved, minus 3. Okay, take it back to home. So you notice my graph is not a V as normal. I can put the other graph on there, y equals absolute value of x. Oop, forgot the x in there. Just click back in, push the X. Blue is my original parent, and the red is my transformation. So it's been moved a lot. It's flipped over. We said that with the negative. It's been moved down 3. I can see that. But it's also been moved to the left 5. But I have an X plus 5. Plus 5 should be to the right. Okay, so that helps me develop a rule. Inside the absolute value, inside a parenthesis, when it's trapped in there by the X, whatever sign I see, it actually does the opposite on the graph. The K on the back, that's not trapped over there by the Y. It's been set free already. Its sign's been changed. Trapped inside with the X, you got to hop out of there, and when you hop out, you take the opposite. So if it says plus 5, you're going to go negatively 5, so that'd be to the left. The one on the back, we're going to keep that sign because it's already been moved out. We're going to keep that. So what I need is my chart. Well, if you need the chart, if you push the little cog wheel, you get the option to chart out these problems. Push the cog wheel, chart it out. And so I see my chart. Well, it just goes -6, -7, -8, -9. I don't get that repeat. But if you look at the vertex at -5, -3, it's been moved over 5 and down 3. So I need to change my chart to mimic that. So I want the middle to be part of the vertex. And then I'm going to count to either side by 2. That's going to be a -4. That one's going to be a -3. Now I'm on either side, and now I see that V. It's -5, -4, -3, -4, -5. I get those V's around the vertex. So I'm going to go from -7 to -3, and then it's -5 down to -3 and repeat. -7, -6, -5, -4, -3, and it's -5, -4, -3, -4, -5. I get that V again around there. So this one right here is my vertex. So 1, 2, 3, 4, 5. 1, 2, 3 starts down here. -6 was at -4. -7 is at -5. -4 is at -4 and -3. So my graph is down here. And the original parent, this was, so my parent, which is y equals absolute value of x, that one's back at our original places, -1, 0, 1, and 2. That'd be 2, 1, 0, 1, and 2. I still get those V's around there. So 0, 1, 2, graphs like this. Graph both. Now describe the change. Well, it's been reflected in the X. It's been moved down by 3, and it's been moved left by 5. It hasn't been stretched or compressed. It goes up 1 over 1, up 1 over 1, up 1 over 1. Goes up 1 over 1, up 1 over, up 1 over 1. It kind of goes up by the same amount, so no compression has happened. Okay. And then there's the word problem. All you're doing is the same thing here. They just do it in words, and they give you a chart to do some graphing, so you're going to estimate what happens at the end after you do this. You should be able to tackle something like that yourself. Just turn the words into the math, write down what you know from the question, and proceed.